Another way to interpret sums of monomial trace evaluations is to use P-excedance-free tableau. Now, P-exceedances are a permutation statistic that we talked about in week 5, which is a long time ago. So let me remind you how they work. So let's recall the definition of P-exceedances, which is from week 5, lesson 3. Let's let U be a P-tableau, and suppose that in some row I we have elements x1, x2, etc. up to xk. And by less than here, I mean in the integers. So we take the posted elements, we're just listing them here in order of increasing elements as integers. But the elements might not appear in this order in the tableau. They might be permuted somehow. So let's let y be the element in position j. So we say that j is a p-exceedance in this row if y is greater in p than the element with the jth greatest index. So normally when we compute exceedances in a permutation, we're comparing letters we see with 1, 2, 3, 4, etc. So here we're going to compare the posted elements we see with the posted elements written in order of increasing indices. Now I'm going to find it convenient to talk about p-tableau of shape n. Let me call that a p-permutation. So we said in week 5, lesson 3, that the statistics p-exceedances and p-descents are equally distributed on all elements, well, equally distributed on Sn. So the number of permutations in Sn such that that permutation has k p-exceedances equals the number of permutations in Sn such that that permutation has k p-descents. And that's true for all p. P doesn't have to be a unit interval order. Now, in particular, the number of permutations with 0 p-exceedances equals the number of permutations with 0 p-descents. And this gives us another interpretation of the induce trivial characters applied to Kai's listed basis elements. Actually, we'll let Q equal 1 for now. So let's let W in Sn avoid the patterns 3, 4, 1, 2, 4, 2, 3, 1. Then eta lambda of the Kai's listed basis element CW equals the number of P-excedance-free P-tableaux of shape lambda. So no row has any P-exceedances. So to see this, note that row semi-strict tableau of shape lambda are just P descent free. Now letting P be the path posted of FW, so I just write P for short. So row semi-strict P tableau of shape lambda are just P descent free P tableau. Of shape lambda, because row semi-strictness just says that when you have one element followed by another element, the second element can't be less than the first in the poset. Incomparable is good, going up is good, but going down is not allowed. So we're just not allowed to have P descents. That's all there is to row semi-strictness. So now that we realize that, we can use the parenthesis erasing bijection from week 5, lesson 3, to convert each descent-free row into an exceedance-free row. Well, each P descent-free row into a P exceedance-free row. Now there is a Q analog when lambda equals n. There's none known for general lambda. But it doesn't exactly follow from this parenthesis erasing bijection. So let's review what we know about the lambda equals n case. Now, first of all, we don't even have a theorem for row semi-strict tableau for a Q analog for general lambda. So eta lambda q of CWQ would be equal to a sum over U row semi-strict Q to some statistic. So the statistic is not known. There probably is a statement of this form that's true, it's just not known yet. However, when lambda equals n, we do have such a theorem. So we do have such a result. So the Q trivial character is just the irreducible character indexed by n. And we have a theorem for irreducible character evaluations that work for all lambda, so they work for one row. And then this is just a sum of Q to the number of inversions in U over all standard P tableau of shape lambda. And this is true because of the relationship between homogeneous symmetric functions and Schur functions. So Sn, the Schur function Sn, is the determinant of the 1-by-1 Jacobi-Trudy matrix that just has H in it. So Sn is equal to Hn. And that means that chi n equals eta n, whether we have a Q there or not. But even so, the bijection from Sn to itself that takes W to sigma of W inverse, where sigma is the parenthesis erasing bijection. So we write a permutation in standard cycle notation, then erase the parentheses and get a one-line notation. So that bijection doesn't preserve inversions. It might map it to something else, so maybe this inversion statistic becomes something on the other side of the bijection, but nobody knows what it is. So we could ask, what statistic does P inversions turn into after the bijection? That's an open question. So, nevertheless, something sort of miraculous happens. there's sort of a miraculous statistic that works well with P-excedance-free P permutations. So we have, if we apply the trivial character of the Hecke algebra to the Cauchy-Damn-Lipschitz basis element CW, we get a sum over U of P exceedance-free P permutation. Here again, to economize notation, I'm writing P for P of FW. Q to the number of inversions in U. And here number of inversions is just the normal symmetric group inversions, where we forget about the post set. All right, to see this, I'll give a slightly sketchy proof. So first, we claim that U is a P-excedance-free P tableau if and only if U is less than or equal to W in the Bruel order. So to see this, let A be the path matrix of P, well, of FW. And if we think about how the path families work, we see that the product A1 V1 A2 V2 etc. up to AN VN equals 1 if and only if there are paths from source I to sink VI for all I. And this is true if and only if I is not less than VI. Oh, I think I switched from U to V. So this should be U1, U2, UN. There are paths from source I to UI for all I. So this is true if and only if I is not less than UI in the post set P for all I. And then this is the same condition as being P-excedance-free. Alright, so that's just the first part of the proof. So U is a P-excedance-free P-tableau, I should say P-permutation, because I'm thinking of tableau of shape N. If and only if U is less than or equal to V in the Brouwer order. Now recall that the N induced trivial character is just actually the trivial character of the Hecke algebra. And the Cauchy-Johnson basis element corresponding to W is just a sum of TV for V less than or equal to W in the Brouwer order. And the trivial character acts in a very simple way on these natural basis elements TV. So each one of them gets mapped to Q to the length of V. So we get the sum overall V less than or equal to W, Q to the length of V. So V less than or equal to W is the same as P-excedance-free. And then length of W is just the ordinary number of inversions in V. And I guess I switched from U to V again, but that's fine. So this tells us that for each P-excedance-free P permutation, we can just treat it as a normal permutation and take the number of inversions. And that's going to give us the correct evaluation of the trivial character. So let's do an example of this. So let's let W be 2431. FW is this star network. P of FW is, we have 1 less than 3 and 4, and 2 is incomparable to everything. So if we look at the Brouwer order, so I drew this in on my Brouwer order, I found 2431 and I circled it, and I circled everything less than 2431 in the Brouwer order. And then we just have to count the number of elements by inversions. So there's one element with no inversions in the circled set, and then there's 3 with 1 inversion, 4 with 2 inversions, 3 with 3 inversions, and 1 with 4 inversions. So that means that if we add up all the monomial traces and apply that to a Cauchy-Johnson basis element, this is equal to the sum of Q to the length of V for all V less than or equal to W in the Brouwer order, and it also equals the sum over U of PFW, I'll just write P, P-excedance-free P permutation, Q to the number of inversions in U, and P is P of FW. Now for P-descent-free P permutations, we can break this down further. And for acyclic orientations of the incomparability graph, we can break this down further. So a natural question to ask now is, for each K, which P-excedance-free P permutations or which permutations V less than or equal to W contribute to a sum of monomial trace evaluations where we sum only over the partitions having exactly K parts. So this is an open question, and I would certainly love to know. If you think of anything, let me know. Also, if we think about this result, now all of these evaluations added together correspond to all the acyclic orientations. So it's natural to ask, I guess each acyclic orientation corresponds to a permutation V less than or equal to W in the Bourrell order. So how do acyclic orientations of the incomparability graph of P correspond to the set of permutations V that are less than or equal to W? And by correspond, I really mean with the inversion. So how do acyclic orientations of the incomparability graph of P with let's say I'm using K for the number of sources, so let's say P. We're using P for the post set with B inversions corresponding to V less than or equal to W with length of V equal to B. So there should be some correspondence between those. And if we can answer this, then what property of permutations V less than or equal to W corresponds to his acyclic orientation having K sources. So again, wide open. I would love to know the answer to any of these questions. The end.